So, hello and welcome everyone to the 7th lecture of the colloquium series on quantum materials and devices, organized by S.N. Bose National Center for Basic Sciences, Kolkata. So, we started this series this year only, and we have today with us Professor Christian Schonenberger from University of Basel, and the former speakers of the series were like Professor R.J. Kava, Professor Anders Sandvik, Professor Subir Sachdev, Professor Rajiv R.P. Singh, Professor Kamran Behnia, and Professor Hidenori Takagi. So although Professor Schonenberger doesn't need any formal introduction, but I'll ask Professor Anjan Burman, Dean Faculty of S.N. Bose National Center for Basic Sciences, to introduce him. Okay, Professor Burman.
Okay, it's a pleasure to introduce Professor Christian Schonenberger, but as Professor Paul said, he doesn't need any introduction. Just for the sake of formality, he's from Department of Physics and Swiss Nanoscience Institute, University of Basel. Professor Christian Schonenberger holds a degree as an electrical engineer in applied science in 1979 and a diploma in physics in 1986. He did a PhD at the IBM Zurich Research Lab in the group of Dr. H. Ronner and Dr. S. Alvarado. His PhD is entitled Understanding Magnetic Force Microscopy, which was awarded with a medal from the ETH Zurich and the Swiss Physical Society Prize in 1991. Subsequently, he worked at the Philips Research Lab at Eindhoven, at first as a postdoc and later as a permanent staff member. In 1994, he was awarded a fellowship from the Swiss National Science Foundation. Soon afterwards, he was elected to a full chair at the University of Basel in 1995. Since then, Professor Schonenberger has set up a group whose research focus on charge transport in nanoscale devices. He has co-authored more than 80 referred journal publications, and he has participated in several European Union programs and is currently directing the Swiss Nanoscience Institute at the University of Basel and the Swiss NSF Center on Nanoscale Science and Technology. With that, I would request Professor Schonenberger to deliver his talk. Cooper pairs are nice, but split ones are even nicer. Why it is interesting to unpair a Cooper pair. Over to you, Professor Schonenberger.
Thank you very much for this kind introduction. It's a real pleasure for me to give this talk. And maybe I should just say at the beginning that it's true that I was the director of the Swiss Nanoscience Institute, but since 1 month I have given this position to a younger colleague. So I now retired from the Swiss Nanoscience Institute as a director, but still very active in research. Actually, I decided to give this talk it's on Cooper pair, split Cooper pairs. It's because it's a work that we have been following for many years. So it's something like 20 years of research where we looked into these problems once in a while, and then later came back into this, and so it evolved over the 20 years in a very interesting manner. So I would like to share with you this story of Cooper pair splitter. Now let's start. Let's see how this works. Okay. So since the work of Einstein, Podolsky, and Rosen on the completeness of quantum mechanics, we know about the importance of entangled particles, now called E-pair pairs. And in early days, this was maybe one of the first experiments where E-pair pairs are studied in details by Aspe and colleagues, where they looked into a violation of Bell inequality, and they found indeed that these entangled pairs can be tested, can be measured. Now today, I mean, entanglement is a resource for quantum information and quantum computing, and we will try. Well, we not only try to do this in optics, but we now also try to do things along these lines in electronics. So optics people are quite advanced as compared to us doing nanoelectronics, because they have sources for EPR pairs. They're quite standard. So you can use, for example, here on the top left, you see this BBO. It's a crystal where you need. Can you hear me? Is somebody speaking? Okay, there on the top left, you see crystal, which is named BBO. So this, what is used here is a nonlinear process where a photon, a high-frequency photon, usually one photon is used to generate two entangled photon at lower energy. They are polarization entangled. This is one way to generate entangled photon pairs. But there are many more. So you can also use semiconductors, for example, in this work, where there's a quantum well used, and the biexciton can decay, in this case, in two photons, which are also polarization entangled. Interestingly, in such kind of systems, in semiconductor quantum well structures, you can also do this on demand, because you can fill this kind of dot in the middle by gate control, and in this way you can generate the entangled photon pair just by push button on demand when you need it. Now, we also, in nanoelectronics, and we would also like to do things like this and try to produce entangled electron pairs. And I don't have to explain you today for what it is good for, but as I said before, it's a resource for quantum computer. It's used to initialize qubits, and it's used for certain measurement protocols. Now, in electronics, maybe the first time people have generated such kind of entangled EPR pairs is in semiconducting quantum dots, which you can see here schematics on top, which you see some gate structures, and then these two circles indicating two quantum dots. And if they each carry one electron, then you have a qubit which has a spin. It's a spin qubit. And then if you couple these two quantum dots, if there is some tunneling coupling in between, then the system is it goes into a molecular state, and this molecular state will have different energies for, let's say, for a symmetric or antisymmetric orbital wave function. And it is a way to generate a singlet pair in the ground state. Now these systems have been studied, these spin qubits in the early work by Daniel Loss, how one can use this to make quantum processes. Today, it's quite standard to make a double quantum dot. This would be such a simple system where you have two electrons with two spin qubits, so to speak, in a semiconducting on two-dimensional electron gas system, so that the structure, the structure you see, these are gate lines on top, which are depleting an electron gas underneath, forming two quantum dots in the middle with these white points here. You can couple them strongly or weakly, or decouple them by this middle gate. You can also form double quantum dot in other systems. So this is on the right, you see very fine, faintly carbon nanotube, very thin electrical wire semiconductor, which you can also gate with some top gates here, which you see. And this is the system where we define the quantum dot here on top and another one on the bottom. And we can control the tunnel coupling with this barrier gate. So this is essentially some basic system which mimic sort of the a single electron, like in a hydrogen atom. When you bring them close together, it forms a chemical molecule, hydrogen molecule. This is something you can play with in such electronic systems, and in the ground state it would be a spin singlet state. So it's a way to produce an entangled spin pair, in a sense. So you could, and people have done this, you could start like this with a double dot where you open the barrier in the middle. So you have left dot and right dot, and you make a potential, the gate such that there is a low potential well on the right, much lower than on the left. Then the two electrons will go to the right and form a spin singlet, a paired electrons and an anti-parallel electron state. which we will call the singlet 0-2 state, because 0 is no charge on the left, but 2 on the right. And then if you go on, you can now put the potential as symmetric, then one electron will go to the left. And now you have the singlet state in the 1-1 configuration. And now you can, with a gate, you can make a barrier here. You separate the 2 electrons, and afterwards you can push them by a voltage pulse or so into some leads. And that would be a pulse sequence, how you could generate also on demand singlet electron pair, which is an entangled spin pair in an electronic system. So this could be seen as a source of entangled spin entangled electrons. This is one way you can do this, and it has been done like this, but it's not the thing we have been working on ourselves. So we got actually very much excited by superconductors, and superconductors have naturally, I mean, the standard BCS superconductors, there the electrons are paired this Cooper pair is a singlet, a spin singlet state, and we were asking the question, could we use these Cooper pairs to do the same? And this question arose maybe more than 20 years ago, let's say 23, 22 years ago. And the conceptual idea was called an Andreev entangler. Conceptual idea is indicated here. You take a superconductor, BCS type superconductor. I mean, they have these Cooper pairs, and what you want to achieve, you want to have these 2 normal leads where you can now send out 2 electrons of the Cooper pair. So 1 electron of the Cooper pair goes to the left arm, and the other electrons to the right arm. And in this way, you convert this this orbital wave function term of this Cooper pair into some propagating modes in the lead. So the N1 is the lead on the left, and N2 is the lead on the right. This is the orbital wave function, symmetric, and the spin is a spin singlet term. So in this way, you would generate 2 flying qubits, 2 electron spins, which are, they're correlated in a spin singlet way. Now the question is, how can you achieve this? I mean, in principle, how good can you do this? How can you do it at all? That the Cooper pairs kind of splits in such a way that 1 electron goes left and the other one goes right. And the first time experiments along these lines have been done is about 2000. There are people call this cross and Andreev reflection, and they were not having quantum dots at that time or things like this. So they're just simple metallic structures. And the first experiment looked like this. There was a superconducting wire with Cooper pairs, and people put normal contacts, let's say some separation, not too far apart, and they were trying to see, is there any correlation in the current on this side relative to what flows on the other side? And has this something to do maybe with the Cooper pair in the middle? And the way, I mean, you can think about it, if a Cooper pair really splits, then you will get sort of simultaneously an electron on the left and one on the right. So you have some kind of positive correlation between the 2 arms. Now, to describe this more in a quantitative way, because now comes the term Andreev reflection, I should quickly introduce this to you. So this is a slide where I try to explain this. So Andreev reflection is a process where we think the other way around. Before, I was thinking you start in the superconductor and you transfer electrons to the normal state. Now we think the other way around. You start with electrons in the normal system and ask the question, how do they get into the superconductor? Now, if an electron comes here from the normal side to an interface to a superconductor, then it cannot, at low energy, low temperature, and so on, it cannot enter the superconductor if this is a good superconductor with a hard gap, because there is a gap for quasi-particles. So what happens is there are 2 possibilities. The electron just reflects away as such, or the electron pairs with another electron to make a Cooper pair. And if the electron is doing this process is called Andreev reflection, then actually, because it takes another electron to make the Cooper pair, as a consequence, a hole is formed, and this hole is propagating away. So the electron is transferred. People say the electron is converted into a hole, and that's called Andreev reflection. But in fact, what happens is 2 electrons paired together into a Cooper pair. And you can also see it this way, that the 2 electrons paired together, 2 antiparallel singlet paired together into a singlet Cooper pair. Now, in this direction, it would be, you could call this Cooper pair formation. And in the opposite direction, it's the same picture. Now a Cooper pair just splits into two single electrons. So this is, you could call this inverse Andreev reflection, or so we call it kind of, when we split it really in space, we then call it Cooper pair splitting. Now, you should know that the Cooper pair is not localized. I mean, it's a wave function, it has some extension, and it's not a nice drawing here, sorry. So there should be some sinusoidal type of decaying function. And this function, this wave function, has an extension of about, it's called the coherence lens. And in aluminum, which is often what we use, this can be quite large, several hundred nanometers. In other superconducting, maybe small, maybe 10 nanometers, something like this. So since that has some extension, you can also think like this, right? You can also think that this process still may happen, that one electron is leaving sort of like more on the left and the other one further away on the right. And if this happens, you can also remove the middle part. Like you can also think about this. And then essentially you have your Cooper pair splitter. Right. So you see already now, you cannot put these two arms too far apart. If you put them further apart than the coherence lengths, then there will be no Cooper pair splitting possible. There will be no correlation anymore. So the length is an important parameter here. And people have been, theorists here have been looking into this initially. And in early papers where they looked at the essentially three-dimensional superconductors and looked at correlation functions from such theories, then actually it turns out that the probability to get such a pair, I mean, would have an exponential decay. That's easy to understand, that these lengths, you know, if you go, this wave function has an exponential decay with the coherence length psi, and therefore there's this exponential factor with the length L. But unfortunately, there's also a prefactor which is actually much more worrying than this one, because you can, if psi is a few hundred nanometer, we can maybe have 100 nanometer, then this is not a problem. But these prefactors in the early theories, they contained here that this is the Fermi velocity K vector of the metal and superconductor, which was metal, aluminum. And an aluminum Fermi wavelength is very short, like 2 angstrom or so. And L is on the length of 100 to 1000 angstrom. So this factor is it's very large. What is here? It's 1 divided by 1000, and this one is mean free path. There's also some other factor of 100 and so on. So there's a very strong suppression factor in front. And that actually led to the conclusion that, that this prefactor maybe could only be 10 to minus 5. So very small. So why bother if it's so small? So interestingly, people still tried to do this experiment, although the prediction was it was very, very small probability to see something like this. And and the question was, is it really so small? And there were more proposals then following also in theory that one can probably enhance this with some tricks, with using quantum dots, using energy filters in the arms, maybe using magnetic filters, ferromagnetic arm detectors, and so on. So I will not go much into this. We'll come later. Later we will see some important. I will explain in particular the one with the quantum dot, because that's very important contribution. There were also people talking about carbon nanotube, etc. So essentially, in the beginning, around 2005, the question was all about how efficient could this be? Is it really small? And you could also think this is another term of thinking that's following Marcus Whittaker, the late Marcus Whittaker. He would have made the drawing like this, would say, okay, I take a superconductor, I attach a beam splitter. For him, a beam splitter is kind of a cavity where electrons come in, they scatter around in the cavity, and then they have 2 outgoing leads. Now the question is, how probable is that you get, 2 electrons tunnel in here into this cavity? They can now, 1 electron can escape on arm 1 and the other one on arm 2, but obviously they can also escape at the same arm. So in this kind of simple term picture, you could also draw like this. That's what we like to have, right? We would like to have split electrons, but you can also think that all these electrons, there's a chaotic cavity, there's a lot of scattering, and obviously they can also do this. They can come out both on the left arm, but they could also come out both on the right arm. And this we will call the direct pair current. We will also see such current in experiment. And the question, and it is possible actually that this pair current, this direct pair current, is larger than the split current later. So in this simple picture, when you would say this just randomization in this cavity, you would expect to have at least only 50%. The maximum for split current in this kind of picture, 50% could be possible, which is much more than the 10 to minus 5, which I told you before. So let's come to experiments. How can we measure that there is? I mean, we somehow have to detect that there is some splitting. And a very interesting approach is that what we did in these Nature papers some time ago is when we look at this problem, and you would think that you have some tunnel coupling here, some tunable coupling of the arm to the left to the superconductor, and also some coupling which you can tune on the right, which are described now by some transmission probability. So this is the transmission probability for electron tunneling on the left, and this is on the right. Now, if you can tune them with some gate voltages, then you can do the following. So first of all, you should recognize that if 2 electrons tunnel to the left, it's always a 2-electron process. Then you have the current will be proportional, the direct pair current, to the probability squared, TL squared, TL times TL. And for the split current, it will be TL times TR, because the other electron goes to the other side. And on the other side, it's just like TR or the same mixed term here. And now what you can do, let's say you do the following: you measure the current in the left arm. Right? You apply a small bias on the superconductor, you measure the current here on the left arm, but you tune the transparency on the probability on the right arm. And now you ask the question, is this current dependent on this right transmission probability? And you see the direct term is not dependent because it only depends on the T left. But the split current depends on the transmission probability on the right. So it shows a correlation. And actually, if you open here more, so if you allow higher probability for an electron to tunnel here, the current will also be enhanced on the left side. So it's a kind of a positive correlation, you see. So that's one way we will use this. I will show you experiments along this line just a little bit later. But the first experiments in the Beckmann, this paper here, 2004 at the bottom, 2004, they didn't have any tunable, they didn't have semiconductors, so they couldn't tune anything, so it was all metallic. And in these metallic structures, what they then did is instead of applying a voltage, instead of looking at the current to the 2 arms, they put this to ground and just put the voltage on a normal contact. And they were asking the question, if you only would have pair current, it would just flow a current through here. But they were just asking, is there some part flowing non-locally on the other arm? Or is there, if this arm is open, if there is a voltage appearing, non-local voltage appearing on the other side? So if there's something appearing on the other side, there must be kind of a non-local process taking place. So that was the early experiments, 2004. And I'll show you this experiment quickly. So they used an aluminum, it's a superconductor, they put normal metal contacts, palladium. They also tried actually, sometimes they tried ferromagnetic materials, but they put here tunnel contacts to the superconductor, and maybe in this case, maybe bias this arm here and measure the voltage, for example, on this side, non-locally. Because it would be an experiment like what is indicated here on the bottom right. So you would have an injector which you bias relative to the ground, so current will flow in. Now you ask, is there something detected on the other side? If it's open, if there is a voltage appearing. Now you can see if there is an electron going in and a Cooper pair would be formed, then actually the hole should, if it's a non-local process, this non-local cross and draft reflection, the hole should appear here. It's non-local and draft reflection. And it means if there's kind of a Cooper pair formed, then actually you will see the opposite charge than here. So in actually Cooper pair splitting or Cooper pair formation would show up here as a opposite voltage, as a negative signal relative to the voltage you apply on the source. So people are looking for this negative signal, and actually it turned out that they most of the time found the wrong sign, a positive signal. I can show you one experiment. This is such an experiment done by Russo and co-workers in Delft. And what they see, this is the non-local voltage, the different temperature. At the lowest temperature, you see it's small bias. It's a positive non-local voltage. And you expect a negative non-local voltage for splitting. And it was quite surprising in the beginning, but it's easy to explain because what I see is another process which is called co-tunneling. What can also happen is that the electron doesn't form a Cooper pair. It just tunnels through. Essentially, you can see this gap. I mean, there's a gap there. You can see this as a tunnel barrier. So the electron just tunnels through the superconductor to the other side, and then the negative charge appears here. So the same sign, and then you get a positive non-local signal. So this is explained as people call this co-tunneling. So this is not what we want, but you see there's a very strong wrong sign, co-tunneling. But if you go at larger bias, for some strange reason, it becomes negative. And so they were claiming that they see some Cooper pair splitting appearing at higher biases. So here's the explanation for co-tunneling. So for co-tunneling, you have one normal contact is biased, and the electron just tunnels essentially. You can see this as it goes through a virtual state in a superconductor, and then it just tunnels into the other side. So that gives a positive non-local voltage, or the other process is actually a hole is generated here, or a Cooper pair is formed. One electron is taken from the left lead and the other one from the right lead. Okay, there is some understanding why we have this elastic co-tunneling here at zero bias, but it's discussed in the theory paper, but I will not go into this. I just show you our own experiments because that was the starting point for us. So let's try this experiment as well. So we built in a PhD work of Andreas Klein, and we built similar devices. So it's an aluminum strip, and there are normal metal palladium contacts with some aluminum is oxidized with a tunnel barrier. So you have these different contacts of different widths. You can measure distance dependence of non-local signal. And we were doing exactly this experiment. We biased, say, contact 1 to the superconductor and measured the voltage non-locally on the other contact. And we have done many of those experiments. And the only parameter which we could change was, I mean, the distance obviously is a parameter which we could change, but we could also change the tunnel barrier. We could oxidize more or less. And then if you oxidize more, I mean, then it gets a higher ohmic tunnel contact. If you oxidize less, I mean, it's a bit more transparent. So, but this parameter you cannot change by turning it up. You just can change by making samples, many samples. So this guy did many samples, and this is just a summary here, which you see. We see. I show you three graphs. I mean, I don't know where my mouse is. So let's look at the one on the right, sample C. This is one which looks very similar to what I showed you before. At small bias, it's elastic co-tunneling dominated. At larger bias, it gets slightly negative, right? Here, I mean, the mouse is now not visible. Here, now here, negative. Now there's the next one, sample B. You see it gets more overall negative, and sample A, everything is negative below the gap. So here we have what we wanted. Essentially, even at small bias, there is dominance of Cooper pair splitting, or this non-local Andreev reflection is happening here, and the question is now why is it here and why it's not there? And it actually turns out that it works much better. You see, the only difference is the tunnel resistance. For lower tunnel resistances, it starts the splitting becomes dominant. Whereas for large tunnel resistance, actually the environmental effects of the interaction in the environment actually suppresses this Cooper pair splitting. This we very well understand at the moment why this was like this, but now we can look at the magnitude of the signal. So here you see, right? It's a non-local signal. It's expressed now in the resistance is 1 ohm here, minus 1 ohm, but the total resistance is about a kilo ohm. So the signal is 1 ohm in 1 kilo roughly. So it's 0.2%. So we found in all these experiments, we found some splitting efficiency of around 0.1, 0.2%. Okay, so it's small, right? I mean, it's 10 to minus 3, but it's larger than actually it has been predicted. Okay, so the red thing says from this experiment, well, we somehow have to play with the tunnel probability, with interactions, they play a role, and so it would be good if we could tune this in a more better way. Here it was very difficult. The tuning is done by replacing samples, by making more samples. But you should really, I would like to emphasize already at this point, that for us, this was already a surprising result. So theory predicted 10 to minus 5, and we already found 10 to minus 3, which is 2 orders of magnitude more. So that was already very promising. And then came the question, can we do better? And yes, we can do better. There was this theory, this proposal, which is here from the LOS group in Basel. They said, look, you have to put in some quantum dots in the middle, and you have to control, this will allow you to control the splitting by using charging effects. So these green dots, quantum dots, they are such that there is some charging energy. So if you add an electron into this dot, it will have to be charged by 1 electron more. If it was empty before, it has 1 electron and gives some charging energy, which is given by charge squared, E squared, divided by the capacitance. And capacitance goes, so the charging energy goes with charge squared. And now it's easy to understand. So if 2 electrons have to go to the dot left, you charge twice. So it's 2 electrons squared, it's 4. If the 2 electrons go to separate dots, then each dot is singly charged. It gives E squared divided by 2c times 2. So it's half the total energy. So just by Coulomb repulsion, essentially what happens now is that Coulomb repulsion forces the electron to split. And therefore the proposal was that's what you have to do, and then you can enhance the splitting. And actually that's what we did. And we actually used for this the nanowires, semiconducting nanowires, which we got at that time, and we still have strong collaboration with this team here from Niels Bohr Laboratory in Copenhagen, Jesper Nygaard's group. So indium arsenide semiconducting nanowires, we put the superconducting aluminum contact in the middle to proximitize superconductivity into the nanowire. We defined 2 quantum dots, one on the left and the right, with this indicated red and green. Defined, we can control it by some gates, which is shown here in yellow. And this is an energy diagram, and you can immediately understand. So if what we can do in a quantum dot, we have kind of discrete levels. So if we position this discrete level, like here the red one, in resonance with the Fermi energy of the superconductor, and on the right side as well, then essentially the electrons it can tunnel freely. One can tunnel to the left, and the other one can tunnel to the right. And that doesn't cost any energy. But they cannot tunnel at the same time to the left, together. This will be suppressed. Okay, so this is a characterization to confirm that there is superconductivity induced. I will not explain this here. Let's just go to the experiment. And the experiment we do is exactly what I explained to you before. So you can think about that the quantum dot is a tunable, it's a level you can move. The level has some width, and so if the level is resonance, there's a larger transmission probability. If the level is more off resonance, there's a lower transmission probability. So with the gates, we can control transmission probability in this arm, and we can also control it in that arm. And now we do exactly this experiment. We measure here the current, but we don't tune the transparency, the transmission probability here, but we tune it on the other arm. So we tune this gate here. And we ask the question, is this current dependent on the transmission probability here? And this will give us the non-local contribution. And in experiment, the experiments are not so simple as theory, because there's also an electrical crosstalk. If you apply a voltage here, there's also just a capacitive coupling to the other gate. So there's also some coupling here directly to the other side. But that's a linear term here in the experiment. So when we measure conductance, it's indicated here, which we can subtract. And so the experiment looks like this. So we position, this is the left dot, this is the resonance of a single state in the left dot. We we fix this gate somewhere here, here actually. And then on this, and then we don't change this gate anymore, we change the other gate, the green one. Now we sweep the green one and see our conductance, we see conductance variation, so the conductance depends. The conductance on the left dot depends on the gate on the right dot. Sure, there's this slope here. This you have to subtract. That's just an artifact. But there's a signal on top. And if you subtract this background and enhance the signal, it looks like this. So this is the signal. This is the non-local signal which we measure. And if you plot it against the conductance on the right arm, just measure from here to here, this is the green curve, you see there's a positive correlation. So if on the right arm transmission is large, then also the non-local signal has large signal. And if the transmission is small, the non-local signal has a small signal. So it's positive correlated, and it's exactly what we expect for the cascade. So that was a great result. And now you can also look at the amplitude, and you see the red signal amplitude is of order, a couple of 10 to minus 3 G0, and here it's of order G0 or something like this. So again, we have here maybe a signal of 10 to minus 3, and can actually, I will show you some results afterward, temperature dependent. But we can convince ourselves, and that's an important thing, that this is due to superconductivity, what we see. It's how easy, we just turn out, we switch, put a magnetic field and switch off the superconductor, and then we can look at what happens in the normal state. And this positive correlation should disappear. And here's a simple explanation. In a normal state, you can think just of resistors. I mean, it's a resistor network, so there's some lead resistor here, and then the quantum dot has some resistance R1 and R2. And if you look at such a network, and you measure the current here, this current here on the left, and you tune the resistance on the right, like if you make the resistance smaller on the right, there will be more current flowing to the right, but then there will be less to the left. And so you will be, in classical circuit, you can simply convince yourself that it's anti-correlated, and it's shown here with a minus sign. And we know all these resistance values, so we can even predict how it should look like. And that's indicated here. This gray curve is how it should look like in the normal state. And above, I show you the result in the normal state. So the red measurement is, we apply a field of 100 millitesla, it turns the superconductor normal, and then we see this signal here, which is now opposite correlated, it's negative correlated, and it's exactly following the theoretic prediction. So clearly this signal, this positive correlated signal, is due to the superconductor, and we think it's because of Cooper splitting. All right, so you see, we studied also the magnitude of this signal, and it turns out it's very low temperature. You see in the millikelvin range, the highest we could get is around 10%. So now we are much larger than we have been before. So now it's kind of opposite. Now all of a sudden we are the result and say, wow, instead of 10 to minus 5 or 10 to minus 3, we have now 1% up to 10%. 10 to minus, we boosted it up to very large value. So the analyst can ask, okay, why is this equation, what's wrong with this equation? And it actually turns out that this prefactor is dimensional. It depends on dimension, how you proximitize superconductivity. And if you proximitize superconductivity in a nanowire, which is quasi 1D, if you think it's a one-dimensional system, then in one dimension, the wave function doesn't decay. There is no decay. So it's due to the low-dimensional system we are using, which ensures that this factor is not active, and that's why we have such a large splitting. Now we can turn the thing around and say, if this factor is not here, and we have our distance is smaller than psi, or much smaller than psi, we should get 1. So now you can ask the question, okay, so we have 10%, why don't you have 100%? And that's actually the next step. And the question is, why don't we have 100%? And now we say the 10% is low. So why is it low? And I have here a picture for you. And so this is what we want, right? So you want to have the Cooper pair splits, 1 electron left, 1 electron right, and then they go out fully. But this is suppressed. We know this was the initial theory proposal. This will be suppressed by Coulomb interaction on the dot. So we can write it like this. So it's suppressed if the charging energy on the dot is sufficiently large, then gamma is the tunnel coupling to the superconductor, sort of like it has to do with the lifetime of the states. So if this U is large enough, then this will be fully suppressed, really strongly suppressed. But you see, this can also happen. So an electron tunnels, but the other electron stays on the superconductor. It's a quasi-particle. It's a forbidden state, but for not too long. this is possible. The electron leaves, and then the other one decides to go through the left top as well, just after each other. And then you have a leakage. You don't have any splitting, and this leakage you can also suppress this leakage if you make the superconductor gap large. So if the superconducting gap is much larger than gamma here, and it's this state here, this will be very strongly suppressed. It's not allowed anymore. But it turns out in our experiment, delta is afforded gamma, unfortunately. And I have here some pictures also of the process which we want. We want to come from the top left to the bottom right. And the simple picture is that the electrons split by resonant states in the two quantum dots. And obviously this process, which is one of them, where one quasi-particle stays in the superconductor, you see it's above here, it's a virtual state, will be suppressed somehow with 1 over delta. And then the other process where you have 2 electrons in the quantum dot, say on the left side, it adds some charging energy, suppressed by 1 over u. Okay, so after this insight, we had a European project called SEND2, and in this project we wanted to make 100% very good entanglers, such Andreev entanglers or Kuiper splitters, and we tried to make advanced structure using still semiconductor nanowires, but now putting many gates at the bottom or at the top, and with these gates to control the tunnel coupling, the gamma. So if you can control gamma, the gamma coupling here, let's see, you can control gamma. If you can make gamma smaller, for example, by controlling with a gate, then we can suppress. We can also help suppressing this process, leakage current. But it turned out that actually it's not so easy to make these devices with many gates. So one of my students, Jens Schindele, was very successful, maybe by luck, with using a carbon nanotube device. So this is a carbon nanotube device. Superconductor is aluminum in the middle, here shown in green, and it's a dot forms here on the top and a dot forms here on the bottom. And actually, in this experiment, he found a very strong non-local current. I mean, which is shown here as a splitting. So we have there's local current of a pair, but if there's very strong split current, then you have very strong current appearing simultaneously in both arms. And you can explain it like this. Let's assume if the left part doesn't exist, no direct pair tunneling at all. Then you will only have a current if the two dots are resonant. If they're not resonant, then there will be no current. And this is indicated at the bottom. So this would be the conductance on the left quantum dot measured as a function of the two gate voltage. There's two gates, the gates on the left and the gates on the right. And this gate voltage control the two levels, right? The level in the right dot and the level in the left dot. And so now if there are multiple levels, they're following one level after the other. And if you say this discrete position, there's a level resonant on the right dot on one dot, and here's the next level resonant on dot 1, and the red line is on dot 2. And you see where they cross, you would expect conductance speed. So in the ideal splitter, we would just expect to see these spiky peaks if two states are resonant. And then we would actually see the same thing on both sides. And G1 would be looking the same in G2. Because the two currents should be equal, right? If an electron goes left, there's another one going right. And unfortunately, there is always some pair current, which gives some background, which are indicated here by these green bars and these red bars. And that's exactly how the experiment looks like. So this is an experiment where you have this green bar is strong, so that's strong pair tunneling. But you see these spikes here coming up. And on the right, it's much better. The pair tunneling is much more suppressed. The spikes are dominating. And you can see if there is a spike here, this spike here is the same spike as this one, and so on. You see there's some correlation between the spikes, and these spikes indicate very, very strong, particularly on the right side, very strong splitting contribution. And one can analyze the magnitude, and one can search for the best and the highest Cooper pair split signal, and the highest we found was around 90%. So now we went from 10 to minus whatever to 90%. So this was about in 2012. Yes, this is the summary to what to do to get 100% CPS. You need to have Coulomb blockade, good strong Coulomb blockade. You need one thing more if you want to make an entangler. You actually have to make sure that the tunnel coupling is weak on the left. There's not highly probable, so that actually makes sure that the coupling, the delta is larger than the tunnel width here. But you need a fast escape into the reservoirs. If the two electrons don't escape fast, or if this is a bottleneck, then this electron will tunnel and the other one will stay here. And then the following processes will be dependent on the state of this dot here, which is not good, because you essentially want to split them with a dot, and then you want to immediately empty the two dots, and then you have your entangled Cooper pair. Now, if this is the case, then actually you should get Cooper pair splitting 100%, and the conductance peaks should be similar on both sides. Okay, I see now my time is rushing much faster than I thought. So do I have still 5 to 10 minutes? Is it okay if I continue 5 to 2 minutes longer?
Yes, sir.
Okay.
Yes, please go ahead.
All right. So we were looking at these delta G signals, and we're looking at the question: are they equal? That's what we predict. And there are some of these peaks we have seen before where it's really the case. The red peak is equal to the blue peak in magnitude. So this is what we expect. But you see, sometimes it's not equal, and sometimes it's very, very, very strange. So the one dot almost shows no signal, and the other one shows a strong signal. And it was a bit puzzling in the beginning, but that was one could explain this quite easily if one now introduces a full model. So we can look at a model where in the master equation where we consider all these states, empty dots, singly occupied state, doubly occupied dots, left and right. And now we introduce probabilities for splitting here, for tunneling of an electron to one dot. And we also add now interdot coupling. That's now crucial to explain this effect. And also the probability to the normal contact is added. So there's plenty of parameters. And with these parameters and rate equations, you can calculate what you should see. And you see these peaks, which are equal on both sides. If all the parameters are right, you can get very strong signals on both sides with equal magnitude. But we can also simulate this type of things, and the understanding is very simple. So what happens here is that this is shown at the bottom right. So if initially the electron splits into the dot, but you have, and the right electron leaves on the right arm, but the left dot has weak coupling to the normal lead one, but stronger coupling, interdot tunnel coupling, then the other electron on the dot left will tunnel to the dot right, and then leave also in the right arm. Then you see nothing on the left arm. On blue, there's nothing to see. So most of the sig peak will be appearing on the right. So no Cooper pair splitting. But this we fully understand. And so also there's an additional parameters you have to make sure that interdot has weak interdot coupling if you want to have 100% splitting. Okay, so we know how to get 100% splitting, and I think it can be realized. It's more or less straightforward today. It took a long time, I must say, and there is much more one can do. I'll give you now a short outlook. People have been looking into Majorana state in kind of similar system where they have nanowires, superconductors that proximitize the nanowire, and then you have Majorana bound state maybe. But you can also look, there's papers on splitting of Cooper pairs by Majorana bound states. One can look at similar structures, looking at Majorana teleportation experiments in similar systems. There have been proposals to use double nanowires as 2 nanowires with 4 Majoranas to make Majorana qubits, etc. And so I showed you this because we also worked on double nanowires. So this is 2 nanowires here with a superconductor on the left, and the quantum dots are in 2 different nanowires. And the same experiment is done here. We try to split the electrons into one nanowires and the other one to the other nanowire. This was work which we did together with Saigo Tarucho's group in Tokyo, and we have results on this where we also find decent Cooper pair splitting in this kind of system. It's not so ideal because you see, if one electron tunnels to the green dot and the other one to the red, these dots are now close by. So they're strong, they feel the charge, they repel each other here. And so actually will suppress, it's not so ideal for 100% Cooper pair splitting, this geometry. The other one is much better actually. So we also have seen that in order to suppress this leakage, which I explained, you have to make tunnel barriers which are small as compared to, I mean, the level broadening should be small compared to the gap. And we have been working with several groups on nanowires that have built-in barriers. So this is this is an indium arsenide nanowire drawn by a group in Pisa in Italy. And they interrupted with indium phosphide here to make a tunnel barrier. And then indium arsenide again, indium phosphide, so you can make a quantum dot here. And now by this, you can actually, this is much easier with this indium phosphide barrier to control, to make a barrier that is large enough so that you get low tunnel probability and get sharp levels. So we were actually studying this with different wires, and I can just tell you that this is just one quantum, it's a measurement of a quantum dot, single quantum dot, where you see this Coulomb blockade regions, and you see just many lines, and what you see is sharp lines, and you see also it's very, very stable. For people that are working on these kind of systems, they would all say, wow, that's a really stable quantum dot. And it's actually true that these quantum dots are extremely well controllable and stable and reproducible. And we also have, I mean, one way would now be to use 2 of such quantum dots and then put the superconductor in between. And then we have sort of maybe 100% Cooper pair splitting. People have also done experiments in the group here of Monty Heibloom. They measured Cooper pair splitting by noise correlation, and immediately then it follows. The question that immediately follows is if we claim that we have a Cooper pair splitter, and then you somehow have to say, well, you have also to show that you maintain the spin entanglement in the system. So the question is, can you do something on spin correlation and entanglement detection? And that's much harder. And so one way to approach this is you need a spin filter to do spin correlation experiments. So one way would be to use ferromagnetic contacts, indicate some kind of ferromagnetic filter effect. And then you can do what optics people have been doing. So you can try to look. You can do sort of experiments where you look at the correlations for different settings of the polarizers, and you also look at the violations by this of Bell inequality. But then for that you need to be able to not only to have spin filter, you need also to be able to have rotatable spin filter. Now the optics people, they all have just the polarizer which you can rotate, and in electronics this is much more involved. So we're not yet able to assess entanglement, but the next step we have been doing. So the step to measure spin coherent correlations, we've just recently addressed this in experiments which were done by Arunav Bordoloy. He's now a postdoc. He was a PhD student in my group, and Andreas Baumgartner. They mostly worked on this, and it's the same setup with 2 quantum dots in indium arsenide nanowire, but we use as a gate a ferromagnetic gate. It's a permalloy gate which polarizes this dot, and we can put these 2 ferromagnetic gates in parallel state or in antiparallel state. And then by this way we can access it's kind of easy to understand if you put them in antiparallel state, right? Then actually it's more probable that this splitting should be enhanced because the two states already there would like to accept the spin up and spin down. If you put them in the opposite polarization, then you should have ideally nothing. I mean, if the spin filter would be ideal, which it is not, then no current would flow. So, but we don't have ideal polarizers. They're more like 10-20% polarizers of this kind. But then you can still write down an equation to test this correlator in the experiment, and you see this kind of a result of this Cooper pair splitting signal. It's in the red signal is large. This is for anti-parallel configuration of the two ferromagnetic gates, and in a parallel configuration it's lower as we expected. And this is also shown here. So for negative, both parallel downwards, it's small, and both parallel upwards, it's small, and for anti-parallel, it's larger. And one can put this into number, and we found for this correlator here, which ideally would be -1, something between -0.1 and -0.3. So what we can say now is that there is clear evidence that the spins are anti-parallel, but it doesn't, it will also be for a product state like this, an anti-parallel product state. We cannot say anything about entanglement yet, but that's the first next step to look into spin correlation. And I hope in the future we'll be able to also control alignment, rotate the spins and do more experiments in these directions. So that's my summary of this work. And there have been many people contributing, and I'm not able to mention them all, and there are actually more than on this slide. And I'd like to finish here. Thank you very much for your interest and for inviting me to this colloquium. Thank you very much.
So, thank you, Christian. So we'll take now questions. First, we'll take questions from the online participants. Okay, so maybe can you help
question
me?
in the chat box.
So online participants, can you please post your raise your hand, maybe, if you have any questions. So there is no question from the online participants. Let me check. Okay. I cannot see any question from the online participants. So maybe now I'll ask offline participants if you have any question. Nobody? Students? So before, like, if some means, I have one question, Christian. So can I ask? So how does it depend on the type of superconductor? Like you talked about only singlet superconductor, right?
Yes,
Can you comment on? Yeah.
I mean, it's a very interesting question. So we were always taking aluminum, because aluminum behaves nice in a hard gap. And so other superconductors may also work niobium, but they're all BCS type superconductors. So some people ask us whether one could use one of these materials where people claim P-wave superconductivity or something like this. Then yeah, it's a possibility. You could do this experiment and see whether there is triplets, for example, triplet superconductivity. But there are few materials that are candidates for this. And
for example, people are sorry. Yeah, please continue.
And usually these materials are not so easy to handle.
Yeah, I know. Yeah. So why I was interested, like people are talking about the superconducting electronics who are making these triplet Cooper pairs, right? So by proximatizing with the ferromagnetic contacts. Now, if you can split these singlet, is it possible to do that, or people have done anything in that direction?
Well, there's some of these some materials which are even without putting, not synthetic, but some of these uranium compounds, so which have which are supposed to be triplet superconductors. So they would have more or less parallel spin would be enhanced. I mean, you would get splitting enhancement with parallel spin. You would detect the parallel component. Should be the opposite of what we do now. So there would be a proof that there is some triplet superconductivity. You could use this device for doing this, but it's very, very difficult experiment.
Yeah, I yeah. Okay, so yeah, thank you. So
Somebody has raised
there
the
is
hand.
so Professor Manoranjan Kumar has a question. Can you? Yeah, Manoranjan, please ask. Yeah.
Yeah. So thank you very much for giving such a wonderful talk. I have one curiosity. While splitting it, just like when we put the superconductors in magnetic field, we get some kind of a FLO kind of phase. So while splitting this, are you observing any FFLO kind of phase or FFLO like structure, like electron arrangements? FFLO is full day ferrule working Ochenkov phase.
Unfortunately, I hear you multiple times, so it's very difficult to understand.
Atin, can you please switch your microphone, because that's what is interfering.
Yeah, can you please write your questions maybe? Yeah, it is not like audible properly.
But Atin, if you repeat it, maybe it will work.
Yeah, maybe can you please say again your question?
Okay, I have just written.
So what he is asking, do you see the FFLO phase while? Okay, just a moment.
Splitting. While splitting this Cooper pair.
Okay, just a moment. Give me 1 moment.
Maybe my answer to this is I don't know much about this.
Yeah. So what he's asking, do you see the FFLO phase while splitting?
The Cooper pair.
No, well, I mean, I was not, this question has never been asked, so I would have to look more deeper into what this FFLO phase is.
Oh, okay.
Okay, probably we can talk maybe later. This FFLO is phase when we apply the magnetic field. Your Cooper pair, some of the Cooper pair like gets disentangled, and they are aligned in the magnetic field, but rest of other electrons are still Cooper pair.
I see. Okay, this is that's a good. Thank you very much for this proposal. It's a very interesting idea. Yeah, we could look actually into this in a paramagnetic field to see what the Cooper pairs are doing. Yeah, but we haven't looked into it. The only thing we were looking is that normal state. We only look magnetic field, use magnetic field to turn into the normal state. But that's true. That magnetic field dependent actually is could be quite interesting.
Okay. Thank you very much.
Thank you for the nice suggestion.
Yeah. Okay. Some more questions? No. Okay. Nitesh, can you please ask the question? Yeah. There is a question from the offline audience here.
I missed, but I did not understand.
I request you to switch off your microphone because that is interfering a lot.
Sorry.
Can you, when you
sorry.
when you have asked a question or suggested something? Yeah. So that's what I wanted. Okay. Yeah, Nitesh, please go ahead. Nitesh, please go ahead.
Yeah. Now, yeah.
So what was the reason for the positive correlation? I missed maybe.
What was the reason for
Positive correlation?
For the positive correlation.
Yes, that is the question. What was the reason for positive correlation?
The reason for positive correlation is that there is a pair, the two electrons which are leaving the superconductor, one to the one arm and the other one to the other arm. That gives positive correlation signal. This is what we test.
And do you have any how does it affect to the superconducting gap if you are splitting the super pair?
Sorry, I didn't get it.
How does the splitting of the super pair affecting the superconducting gap? Is it
How the splitting depends on the gap. Actually, as you have seen, when the gap is large, it would be, relative to the tunnel coupling strength, then it would be better. Because if the tunnel gap is small, then you can have this leakage process where one electron tunnels to one arm, and the other electron tunnels afterwards to the same arm. And it has to stay some time on the superconductor as a quasi-particle. And that is probable when the gap is small. This is quite probable. So you want to have a large gap relative to the tunnel coupling. Or you can say the other way around, you want to have a small tunnel coupling. And then this will be the rate limiting factor. So if you use this as an entangler, and you ask the question, how many pairs can I get to a unit of time? Then the rate limiting factor would be the tunnel barrier to the superconductor.
Okay. Yeah. Thank you. So, any more question? Okay. I don't see any question raised hand. So I think. Okay. So if there is no question, so I thank from the organizers, Professor Schonenberger, for a very nice and intuitive talk on this Cooper pair splitting and giving a summary on the subject. So it was very nice. Thank you very much. Yeah.
Yeah, thank you for the invitation. It was a pleasure to show you this journey. It's a long journey, but it's still not at the end. There's a lot to do.
So next time we would like to see you offline, like not in this hybrid mode.
Sure.
So
Yeah.
It's about time for me to visit you once.
Yeah. Okay. So with this, we end this colloquium. Thank you.
Thank you. Have a good day.